Hello, everyone. Thank you so much for attending my presentation. I'm Lise, a business developer at CILcare. CILcare is a preclinical CRO specialized in hearing. And today I will be talking about hearing loss as a side effect. Ototoxicity targets cochlear and vestibular structures in the inner ear, resulting in hearing loss, tinnitus, and vertigo that all can be reversible or irreversible. Studies reported ototoxicity in more than 200 marketed drugs. Well-known toxic drugs include chemotherapeutics, like cisplatin, antibiotics, like aminoglycosides and macrolides, antimalarial drugs, cyclodextrins, and many more. Today, I will present the examples from three first drug classes. One of the most well-known toxic drugs, cisplatin, is ototoxic in up to 60% of treated children. Gentamicin, on the other hand, is an antibiotic used to treat gram-negative infections, and it is ototoxic in up to 47% of patients. When you hear something, the sound waves travel from the external ear through the middle ear to the snail-like structure in the inner ear called the cochlea. In the cochlea, the here specialized organ of Corti houses sensory cells, one row of inner hair cells and three rows of outer hair cells. At the base of hair cells, here in green and blue, you can see the auditory neurons that receive the signal and transmit it through the auditory nerve to the brain. Ototoxic drugs can damage hair cells, auditory neurons, and the synapses between them. Hair cells do not regenerate in mammals, so once they are lost forever, and the hair cell loss usually means hearing loss. To assess the ototoxicity, we can visualize cells with a cochleogram or measure hearing in vivo using ABR and DPA. ABR stands for Auditory Brainstem Response. It is a functional electrophysiological measure to detect hearing loss. ABRs represent the activity of inner hair cells and auditory neurons. The minimal sound level that animals perceive, the hearing threshold, is recorded for each frequency. On this graph, you can see normal hearing in brown and the pattern of hearing loss in orange, characterized by ABR threshold increase. DPAE, on the other hand, stand for distortion product otoacoustic emissions and represent the activity of outer hair cells. They are recorded as ABR for each frequency, and they are a complementary readout to ABR. Here on this graph on the right, you can see normal hearing in brown and a pattern of hearing loss in orange. And you can see that hearing loss is characterized by a decrease in DPAE amplitude. In most cases, hearing loss is due to hair cell loss. A cochlea is organized onotopically, meaning that high frequencies are perceived at the base of the cochlea and the low frequencies at the apex. A cochleogram is a histopathological analysis to count hair cells along the cochlea and identify a hair cell loss on each frequency. We can then correlate the hair cell loss with the results from ABR and DPA. Let's look at the example. In the pictures here, you can see the fragment of the cochlea before and after noise exposure. As you can see at the top picture, you may notice one row of inner hair cells at the bottom and three rows of outer hair cells on top. After noise exposure, you can see that there are hair cells missing. On this slide, you can see an ototoxic effect of cisplatin in rats. Animals received an infusion of cisplatin and underwent necropsy 3 days later. We measured ABI and DPAE at baseline and just before the necropsy, and we sampled their cochlea. In the graph on the right, you can see DPAE amplitude measured before the necropsy in vehicle group in red and in cisplatin treated group in blue. There is a significant decrease in DPAE amplitude in the treated group at 24 kHz and 32 kHz. At the cochleogram, we observed a significant decrease of outer hair cell density at 25 and 32 kHz, matching with DPAE amplitude decrease that we saw earlier. Therefore, cisplatin ototoxicity occurs as soon as 3 days after exposure and targets mostly outer hair cells. To assess gentamicin ototoxicity, we administered gentamicin to rats for 5 days and necropsied the animals at 15 days. We measured ABI and DPA at baseline and every 5 days until the necropsy. On the ABR graph in the center of the slide, you can see the ABR thresholds recorded at different time points. So here in green at 15 days just before the necropsy, in light green at 10 days, in orange at 5 days, and at baseline in brown. So as you can see, there is significant increase in ABR threshold at all frequencies at day 10 and day 15 versus baseline. On the DPA graph on the right, you may see a significant decrease in DPA amplitude at higher frequencies at day 15. Therefore, gentamicin had a delayed ototoxic effect and targeted both inner and outer hair cells. In this experiment, we tested hydroxychloroquine and antimalarial treatment in rats. We administered hydroxychloroquine for 5 days and necropsied the animals at day 38. We measured ABI and DPA at baseline and throughout the study and before the necropsy. In the center of the slide, you can see the ABR threshold graphs recorded at day 24. Here you can see a sham group in brown and hydroxychloroquine treated group in light green. As you can see, there is a significant increase in ABR thresholds in hydroxychloroquine treated group at higher frequencies. At day 38, we again recorded the ABR thresholds, and you can notice that there is a significant increase in ABR thresholds at different frequencies starting at 10 kilohertz. Therefore, hydroxychloroquine triggers progressive hearing loss. To summarize, ototoxic substances, including marketed drugs and drug candidates, can result in irreversible hearing loss that could impact the quality of life dramatically. It is important to monitor potential ototoxicity preclinically with both functional and histological readouts. While developing new drugs, especially in previously reported ototoxic classes, you should assess the auditory safety of drug candidates and excipients. At CILcare, we are committed to auditory safety. We taught a continuous education course at the SOT conference last year, featuring the FDA, and we also recorded a webinar at the ACT conference. If you're interested, you are welcome to connect with us to see the recordings and to talk about ototoxicity. Thank you for your attention.